Okay, good morning, ladies and gentlemen. Today we're looking at something that we've seen before. And if you were awake in honors chemistry, you remember this guy, Gibbs Free Energy. In its mathematic form, it looks like this. Delta G equals delta H minus T delta S, where this is going to be our free energy. This is going to be our enthalpy, otherwise known as heat. And this guy is going to be our disorder, otherwise known as entropy. What we're looking for is a value of delta G that is equal to or less than 0. So a negative value of delta G means the reaction is spontaneous. So let's make sure that we are focusing on that a reaction is spontaneous only when delta G is negative. And what determines that is this final guy. This dude right here. This, of course, is temperature. And let's be careful that we put it in kelvins. All right. Let's try one. So let's make this a little smaller so we can all see this. This is a blast from the past. We've seen this type of stuff many times before. So it says here for this reaction, this is called ammonium chloride, and it is decomposing into ammonia, and hydrochloric acid. Now, let's be honest. Right off the bat, we know that this is a reaction that is increasing disorder. I mean, check this out. We're going from one molecule, which is a solid, to two molecules that are both gases, right? So we know the reaction is going to increase disorder. That's going to help spontaneity. All right, well, check it out. We've got a positive delta S. We've got a value of delta H that is also positive, which means that this reaction actually requires energy. It's not giving it off. It's an endothermic reaction that does not help spontaneity. We're doing this at a temperature of 298.15 kelvins. So let's see what happens here. Delta G equals delta H minus T delta S. All right, so we're trying to solve for delta G. We know our delta H, 176 kilojoules per mole, minus, and we want this entire quantity. So our temperature, 298.15 kelvins. And multiplying that by our delta S, which is 0.285 kilojoules per mole Kelvin. Ran out of space. Well, you know me, I like to do what's in the parentheses first, so let's bust out our calculator. And so we're going to say 298.15 times 0.285. And inside these parentheses, we now have 84.97, and the unit Kelvin is canceled, so what we're left with is kilojoules per mole. Okay, we want this to be spontaneous. It's got to be negative to be spontaneous. 176 minus 84.97. It is clearly not spontaneous. This is a positive number not spontaneous. Boo. Okay. So how are we going to find out whether or not this is spontaneous? And so here's that trick that we remember from last year, is that it's spontaneous if delta G is negative. That means less than 0. So let's take this equation, delta G equals delta H minus T delta S, and let's replace delta G with 0. All right. Well, now what we have is, if we get delta H by itself, now we're going to say that positive T delta S is equal to delta H, right? All I did was subtract negative T delta S from both sides. And that means that T is now equal to delta H divided by delta S. So we can easily find out what temperature this reaction will be spontaneous. All right, so we have all of our values from right here. Okay, we have our delta S, that's this guy, 0.285. We have our delta H, 176. Let's plug them right in. So delta H, 176 kilojoules per mole. We've got delta S, 0.285 kilojoules per mole Kelvin. And what's really neat about this is that kilojoules and moles cancels. Use our answer in kelvins. And so what you get is a temperature of 176 divided by 0.285. 617.5 kelvins. Whoops. At any rate, here is how we determine whether or not our reaction is going to be spontaneous or not. 617.5 kelvins is the temperature at which this reaction is spontaneous, where it starts to run by itself. So once it's hot enough, and that should make some sense too, get those molecules moving, right? All right, so I'm going to ask you guys to try 2 of these, all right? And they look like this. You're going to need to look up some values for delta H and delta S, all right? And so you're going to look for the delta G for the overall reaction. It's going to ask you, of course, is it spontaneous? And you can easily look up the values for delta S as well. And the same thing is true for this guy. All right, where we've got the delta G, we're looking for the overall delta G. Is it spontaneous? And we have values for delta S, and we can look up the values for delta H as well to determine the spontaneity. Okay? So take these 2 for a spin, and I'll see you guys in the next session.